Okay, so this is a problem from recitation, and it's also on worksheet 3, number 3. I believe my original notes actually had a sign mistake, so I'm gonna definitely correct it in this one and then upload these notes over the other ones. So consider a semicircle of radius r with total charge q, so the half ring of charge, and the question is, what is the electric field at the origin? So just like any other problem with continuous charge distributions, the first thing we're going to do is figure out what symmetries are at play, with the goal of removing one of the components, either ex or ey. Next, we're going to set up the integral for E, the electric field, and then we're going to use Coulomb's law for dq to set up the integral in terms of d theta. The intuition behind why we want to write this in terms of theta is because since we have a ring, r is a constant value, so polar coordinates and using theta seems like the natural picture. And as you can see sort of depicted down here, we do this so that we can sweep over from 0 to pi. So let's figure out the symmetries first. I guess I kind of have the answer already written down. If we consider a point on the ring on this left side, I've drawn the picture in terms of two colors to show the left and the right side. The contribution of the electric field from that little particle on the left should be some like down and away component, down and to the right. Let's mirror this picture and look at the same point on the right side. This should give me some electric field contribution down and to the left. So if you remember like the rod problem, just like that, the x component should cancel and we should get a net component in the y direction going down. So in this case, we can solve just for y. Sort of as a quick reminder, if you remember the rod problem, we basically did the same thing. We consider a small point here. It gave us some contribution up and to the left. The mirrored point over there gave us the same thing, but up and to the right. And then the electric field was just straight up, which is why we ignored the x component. So now that we know what part we want to solve for, we can start doing that. So let me redraw the picture. So we know that EY is equal to the integral of all the EY contributions. And we want to write this in terms of DE, like the actual electric field, because working components is a little bit difficult. If we consider a small part over here, the net electric field contribution of the origin is something like this. This is our DE. Then the component that we want is this one. The sort of the y component. If we remember our geometry, we call this angle here theta. And this angle here is also theta. Now I'm going to include a minus sign here. Because this indicates that our contribution is going downward. And I don't want to have to correct the signs later in the problem. So this is easier to add the negative sign here now. So now we should figure out what DE is. I'm going to zoom in on this arc. Oop. And let's consider some small arc length here. I'm going to call this DS. This part DS should give me some amount of charge, so we should figure out how long it is. Imagine this is infinitesimally thin. We can call this little arc d theta, a differential angle theta. And we know that the radius is r. So from this relationship, we know that ds is equal to r d theta. This is just the arc length of this like part of the ring. And then just like the rod problem, we remember that dq, the amount of charge given is equal to lambda ds. We can sort of justify this by remembering that lambda is charge per length, and ds will be a length. But we weren't given lambda in this problem, so we should figure out what it is. So remember that lambda is a charge per length. So in this case, it'll be q over pi r. The reason it's pi r is because we use the length of the arc that we're dealing with. So this entire half ring is length pi r because it's half a circle. And a full circle would have circumference 2 pi r. So now we can make our substitutions. I'm going to pull a minus sign out. So we use Coulomb's law. Remember that dE is equal to k dq over r squared. Conveniently, the distance from the origin to any point on the ring is just the radius, so that stays the same. Remember, so k dq over r squared. We now know what dq is. And I'm going to replace now ds, but I'm going to keep my answer in terms of lambda just to keep the notation simple. So I've canceled out one of the r's. Just note that while I'm going to do this problem in terms of lambda, if this was an exam at the very end, you should definitely substitute what lambda is if it wasn't given. So now I'm going to pull out all the constants. So k, lambda, and r have nothing to do with theta. I get an integral of sine theta d theta. And if we remember the way we're sweeping is a half circle. So theta should go from 0 to pi, or 180 degrees if you're going to work with degrees. So now solving this integral, the integral of sine theta should be minus cosine theta. This is going to be evaluated at 0 to pi. I'm going to cancel out the negative signs. Then evaluating this should give us cosine of pi minus cosine of 0, which is minus 1 minus 1. So we get that EY is equal to minus 2k lambda over r. Or if you replace out what lambda is, minus 2k over r q over pi r. Or minus 2k q over pi r squared. Just to show you that this matches with the solution given in the worksheet notes. We remember what k is. So k is 1 over 4 pi epsilon naught. So this will give us minus q over 2 pi squared epsilon naught r squared. So then the net electric field, because it needs to be a vector, is minus q over 2 pi squared epsilon naught r squared, the y hat direction. So we should gut check this and make sure it makes sense. Let's assume that q is positive. If q is positive, the net electric field should be downward. And in this case, this quantity does exactly that. So net field is downward. And this is how you solve the arc charge problem. Now that you've done this one, I can recommend some other problems you could try. So basically different variations of the arc of charge. So one problem you could try is two arcs of different charges. So here on the left, I have a quarter circle of plus q and another quarter circle of minus q, both the radius r. And you can try to find the electric field at the center. Or you can do one in which you have one in the second quadrant and one in the fourth quadrant. You would solve this basically the same way as you did the problem we just did, except you would do two integrals, one for each part, and then use the principle of superposition to add them together. Another problem I'd recommend, this is actually in Wiley Plus, is a line bent into a charge. So imagine I give you a rod of length L with some charge Q, and then I bend it and tell you the radius of the new arc. Then I would ask you to find the electric field at the center. Again, this is very similar to the problem we just did, except now you would have to figure out what theta is you'd have to integrate over. Another problem that invokes a symmetry is if I took the half ring and I rotated it by 45 degrees or pi over 4. In this one, in our standard coordinate system, you would now have an x and a y component. But maybe the easiest way to solve this is to rotate your coordinate system by 45 degrees, solve for one of the components, and then rotate it back. And then finally, once you know how to do all these arc problems, you can do any arbitrary arc of length. Any arbitrary arc length of charge, any arbitrary arc of charge of some length L. So we give you a theta and give you an R, and you can solve for the field at the center.